Next, we will talk about the optimal binary search tree problem. Before we do so, let us review what is a binary search tree. Let S denote a set of n ordered items. So it could be like n numbers or n words, and then they are ordered like in lexicographical order. A binary search tree corresponding to the set of items S is a certain tree, is a binary tree, let's call it T, such that there are exactly n nodes in T, one node corresponding to one item of S. And for any node inside the tree, items appearing on the left of V will be smaller, and items on the right subtree of V will be larger than V. So we have the following example. So for instance, there are 6 words that we have, and then this represents some food, and then this is a certain binary search tree for these 6 words, so we assume that they are arranged in lexicographical order. So if we take a look at the root node, this is hot dog, so we will see that any value appearing on the left subtree of this hot dog will have values smaller than hot dog. And similarly, anything on the right side of this hot dog will have values larger than hot dog. And this is true for every node. So for instance, this banana, so for banana, anything appearing on the left side of banana is smaller than it, and on the right side it is larger than it. But the binary search tree for the same 6 words is not unique, so we could have a very different looking binary search tree for the same 6 words. So again, we see that banana is here, on the left side, values are smaller, on the right side, values are larger. And then if you look at this pizza, on the left side, these are values that are smaller, and then on the right side, the values are larger. Okay, now the purpose of setting a binary search tree for S is to allow us to do searching on the items of S. And then, how do we search a certain item? So, for instance, if we want to search hot dog here, we simply compare the word hot dog with the root node here, and then we find out that, oh, hot dog is larger than this value. So we can now focus our search on the right side of this tree. So when we focus on the right side of this tree, then we will compare hot dog with pizza, and then we find out that hot dog is smaller than pizza. So we can focus the search on the left side of this node. So in that case, we go here, and then we now compare the root node here with hot dog, and then we find that it's there. So to do the searching, the number of comparisons that we need to search for an item X is equal to the number of nodes on the path from the root to the node storing X. Now normally, when we store a binary search tree, we will look at the worst case, and the worst case will be at least omega of log of n. But now, for this discussion today, we will consider the expected case. So what do we mean by expected case? So here, let's say T is a certain binary search tree for S, and for each item X, let's call it Xj in S, we will let Fj to denote the frequency of Xj to be searched. So let us say we have already got some statistics of how many times that Xj will be searched. And Lj denotes the level of Xj inside the search tree T. So the level here is defined in the following way. We assume that the root node has level 1, the child of the root is level 2, and the child of a root is having level 3, and so on and so forth. Now our target, so what does that mean? So Lj is equal to the number of comparisons if we want to search Xj inside the search tree T. So our target is to find a binary search tree such that F1L1 plus F2L2 blah 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 up to Fnln, the summation of all these terms, is minimized. So the meaning of this summation is equal to the number of comparisons. Suppose that we are searching F1 search on X1, F2 searches on X2, and so on and so forth up to Fn searches on Xn. So this is the number of comparisons among all the possible searches that we are going to make. So we could have different search tree T, and with different search tree T, the level L1, L2, L3, and so on and so forth will be different. So we want to get an optimal binary search tree such that this term, the summation term here, is minimized. So we are not going to give you the how to do so, but we are going to give you some hints of how do we design. It turns out that this optimal binary search tree problem is very, very similar to the matrix multiplication problem that we have just studied. So in order to do so, we may find the optimal binary search tree by thinking backwardly. In particular, what information we wish to know in order to determine what is the best item to store at the root. Now remember, in the matrix chain multiplication, we are trying to find out what? We are trying to find out what is the last operation that is going to give you in the best sequence. And here, we want to find out what is the best item to store at the root in order to get the best optimal binary search tree. Now suppose that xk is the best item of the root. We don't know which xk it is, but then we can try every possible cases. But suppose that xk is the best root. Then in that case, in order to know how good the performance of the tree, or what is the total search cost if xk is put at the root, then we will need to know what is the optimal binary search tree to handle all the objects, all the items that is smaller than xk, because they are going to put it in the same subtree, the left subtree of xk. And similarly, we want to get an optimal binary search tree to handle the values for xk plus 1 up to xn, because they are going to be stored on the right side as a right subtree of xk. So I hope that you can somehow see that there are a lot of similarity between this problem and the matrix chain multiplication. So yeah, good luck.